Hello students, I hope that you are good, well and fine. Today we will be continuing our discussion. Today we will be continuing our discussion on NCERT Miscellaneous Exercise, Chapter 1, Class 12th. What chapter? Can you name it? Indeed, it is Relations and Functions. We discussed 1 to 4 problems. Now we will be discussing 5 to 7 problems in this today's lecture. So let's move to our fifth question. So fifth question, what it says: let A is this set with elements -1, 0, 1, 2. Set B is set with elements -4, -2, 0, 2. F and G both defined from A to B. B functions defined by, so F is defined by x square minus ax, where x belongs to the domain which is A, and gx is defined by this, where x belongs to the domain of G, which is the same as the domain of F, which is A. Are F and G equal? So when do we say that when do we say that two given functions are equal to each other? When do we say that? First, if equality of relation happens, relation happens. What it means? It means that if I have two relation, say R1 and R2, then every pair in R1, AB, must have every pair in R1 must have an identical pair in R2. In R2. And the second property was equality of codomains. Equality of codomains. Both the relation R1 and R2 have the same codomains. So in short, what you can say, that the function f from A to B and G from A to B, as you can see, the codomains are same as well as the domains. Because if you saw this point, what this says, that every pair in this set, every pair in this relation must have identical pair in this relation. And we know, what do we mean by domain in relation? So domain is the set of all first elements in the pair. So set of all first elements in the pair, we say that it is what such set is called as the domain of the relation. So this means if every pair must having the identical pair in this means the domain for this set is also going to be the same as for this set. And vice versa also, every pair in this relation must have an identical pair in this relation. So this that's why we wrote f. If f is from A to B, then G is also going from same domain to the same codomain, as we saw. With this condition also happening, why? So the condition is what? the condition, as you can saw, the two main conditions are the domain and codomain, equality of domain and codomain. Okay, and this the output. Okay, so f of a must equals to g of a for every a belongs to a, as you can see over here. Okay, so let's see that the given functions f and g are equal or not. Okay, so first of all, just g of minus 1, just find out g of minus 1, g of 0, g of 1 and g of 2, g of 2. Okay, so g of minus 1 will be what? We know minus 1 square gx is equals to x square minus x. So g of minus 1 will be, g of minus 1 will be minus 1 square minus 1. This will be 1 square minus 1, 0. Okay. What about g of 0? G of 0 is 0 square minus 0. It will be 0. G of 1, g of 1 will be what? G of 1, if you recall, g of 1 will be 1 square minus 1, which is equals to same as 0. And g of 2, if you can see, 4 minus 2 will be 2. Okay, this is for g. Now let's evaluate for f. Sorry, this is for f. Sorry, so this is for f. Okay, okay, this is for f. Okay, now it's time for g. G is equals to 2 times mod x minus 1 by 2 minus 1. Okay, so now the g of what? G of minus 1, g of 0, g of 1 and g of 2. Okay, so g of minus 1 will be 2 minus 1 by 2 mod of minus 1 by 2 minus 1, and if you solve this, what you will get? Minus 3 by 2, minus 3 by 2. And what we know, that any minus real number, what you will get? The output as x. If you recall, let me give you the proper definition for modulus function. We know that it is modulus function, and modulus function means this, and this is what? Equals to x whenever x is 0 or greater than 0, and minus x whenever x is less than 0. As you can see, x over here is less than 0, so we will write what? Minus of minus 3 by 2. This means 3 by 2, multiply 3 by 2, this means 3, and 3 minus 1 will be what? 2. Okay, now for g of 0, g of 0 means 2, 0 minus 1 by 2 minus 1. Applying the same definition over here, what we will get is 1 by 2, and you cancel the 2 over here and here, you will get 1 minus 1, which will be what? 0. Now g of 1 means 1 minus 1 by 2 minus 1, and 1 minus 1 by 2 is 1 by 2. Using this definition, what it will be? It will be 2 times 1 by 2 minus 1, and we know it is just 1. 1 minus 1 is 0. Now g of 2. G of 2 will be 2 minus 1 by 2 minus 1. If you solve this, what you will get? 3 by 2. Okay, so 3 by 2. Now applying the definition from this, what I can say is 2 multiply 3 by 2 minus 1 will be 3 minus 1. What it will be? Just 2. So now, as you can see, what? If you try to put this, if you try to put this in terms of relation, as you can write that, what you can write, let me clear. Okay, so as you can see that what the pairs, if you try to make pairs, so your F relation will be what, like this. So -1 is related to 0, okay, and 0 also related to 0, 1 is also related to 0, and 2 is also related to 2, not 0 is 2. Now for G, okay, for what you are going to say for G. So for G, if you put G at a -1, so okay, so G for -1, G is equals to -1 to, okay, 0 0, okay, 1 0, okay, and 2 2. This is the pairs indeed. So as you can see, let me calculate once again the value for G of -1. Okay, so G of -1 will be what? G of -1 will be 2 -1 -1 by 2 -1. This will be what? -3 by 2 -3 by 2. This means 3 -1, which will be just 2. Okay. Now, as you can see, what you can see that this pair is here, this pair is also over here, and this pair is also over here, but you cannot find this pair in this relationship. So what you can say? You can say that these functions are not equals to each other. Okay. So as you can see that this pair is not belongs to here. So we can say that it is not what? Not equal to each other. Yes? Yes. Okay. Okay. I hope that you are getting when we say that two functions are equals to each other. Okay. Okay. Let me again go through it. Okay. So that you can have a better idea about the equality of two functions. So first of all, whenever you got two functions, just first of all see that their domain must be same and their codomain also must be same, and then try to, if the relation given to you is just small as like this, the domain is just this set, and the output will be the also small set. So I calculated every output for f1. As you can see, let me see, f of -1 will be as fx is equals to x square minus x, and f of -1 will be what? -1 square minus of -1, you will get 1 square plus 1, so you will get 2. Okay, so I have done this thing wrong, I hope. Okay, so this means it must be 2. Sorry for this inconvenience and this error. Okay, now this thing whole change our perspective. What? Because now this is also what? 1 minus 0. This means that any, as you can see, this pair now also belongs to in this relation G. So this means what we can say? Indeed, these functions are equal to each other. Okay, so sorry for this error I have done. Okay, so it's clear that now they are equal. Okay, so as you saw that nothing worries. As you saw, whenever we say that two functions are equals, we say that every pair in this function must be in this function also. Then only we can say that two functions given to us are equal to each other. Also keep this point in mind that f of a to b, the domain for f is equals to the domain for g, and the codomain for f is also equals to the codomain for b. And from this definition I also say that if you plug f of -1, what you will get? The same output as the g of -1. If you put f of 0, what you will get? The same output f as g of 0, and f of 1 you will get the same output as g of 1, and for f of 2 you will get same output as g of 2. Okay, I hope now it is very clear to you why these functions are equal to each other. Okay, sorry for the error. Okay, let's move next. So indeed, yes, they are equal to each other. Okay, let's move to the sixth question. What it says? The sixth question says that if the set A 1, 2, 3, so my set is A 1, 2, 3, then number of relations containing this. So the number of relation containing this pair and this pair, which are reflexive and symmetric but not transitive. Okay, so let's begin what we are given with. So we have to find out such relations such that this pair and this pair belongs to the relation, and the relation we will going to make must be reflexive as well as symmetric but not transitive. Okay, let's make. So suppose R is my relation. R is a relation from R is from A to A. Okay, so this means I am going to make that first of all this 1, 2 and 1, 3 must be in my relation. Okay, okay. Now because I have to make it symmetric, so this means the 2, 1 elements and 3, 1 elements must be in this relation set. Yes, yes. So now it is symmetric. As you can see, 1, 2 belongs to the relation, then 2, 1 also belongs to the relation, because in symmetric we know if A, B belongs to R, this means that B, A also belongs to the relation R, as you can see over here. Now what? Now it must also be reflexive. For reflexive, this set given the 1, 1, 2, 2 and 3, 3 elements or these pairs must also belongs to the relation R if my relation is going to be reflexive. Okay, so let me put these pairs also. So these are the necessary elements. Okay, now if you see that R is the subset for A cross A. Okay, and A cross A, you know, the A cross A, the total number of elements in A cross A will be what? 9. Yes, and those 9 elements will be what? 1, 1, 2, 2, 2, 3, sorry, 3, 3, 3, 3, 1, 2, 1, 3, 2, 1, 2, 3, 3, 1 and 3, 3. So these are the total 9 elements in this A cross A. As you can see that we use this element 1, 2, 1, 3, 1, 2, 1, 3 and 3, 1. And what element? So here it will be what? 3, 2. Okay. So we used as you can see over here 1, 3 and we use 3, 1, 1, 2 we use this. So the only elements remaining over here are these, as you can see. Yes, so if I am taking this relation, it is reflexive, yes. It is symmetric, yes. Is it transitive? No. Why? Because 1 comma 3, as you can see like this, that where that 1 comma now, so 2 comma 1, if you pick this pair, 2 comma 1 belongs to R, okay, and 1 comma 3 also belongs to R, okay, but you can see that 2 comma 3 doesn't belongs to R, so it is not transitive. Okay, so we have constructed a relation such that it follows reflexivity, symmetric relation, but not transitive. Okay, so I have found out one such relation. Okay, can I make another one? Let's try to make it. So these are the necessary elements. Okay, I cannot remove any of these pairs. Yes, because if I remove any of these, it will not be either reflexive or not symmetric, but I want that it must be reflexive and symmetric. Okay, so what I can do is just add elements. Okay, and what other elements I can add? I can either add this one and this one also. Okay, if you try to add this element, then what will happen? Just add it. So 2 comma 3. So now what? So in order to make that my relation must be symmetric, then 3 comma 2 must be in there. So 3 comma 2 must be in there. If this happens, then it will be what? Transitive also. So this, I cannot add these elements. So the only possible relation I can make is this one. So the number of relation containing this pair and this pair, which are reflexive as well as symmetric, the answer will be just one relation. Okay, I hope that it is quite clear to you. So answer is A, 1. Let's move to next question. Now next question, what it says, and this will be our last question for this lecture also. So A set is given 1, 2, 3. Then number of equivalence relation containing this pair. Okay, so we have to find out equivalence relations containing just this pair. So let us what construct. Okay, so equivalence relation. First of all, we know that relation must be subset of A cross A. Okay, now what? And we know the total number of pairs in A cross A will be what? 9. And let me write it down. So A cross A will be what? 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, 3 comma 3. Okay, now what? Now first of all, the necessary thing in our relation is this pair. So this pair must be in our relation. So let's put it. Okay, now what? As my relation will be what? Equivalent. So this means it must be reflexive, it must be symmetric, it must be transitive. Okay, if it is reflexive, then if it is symmetric, then if 1 comma 2 belongs to my relation, then 2 comma 1 also belongs to the relation. Okay, so symmetric now satisfied. Okay, what about reflexive? In order to be a reflexive relation, these pair must be in my relation. So let me write it down. So 1 comma 1, 1 comma 2, 1 comma 1, 2 comma 2, and 3 comma 3. Okay, now what? Okay, so far so good. It is still reflexive and symmetric, as you can see, but it must also be transitive. So 1 comma 2, 2 comma 1. So this means 1 comma 1 also belongs to, yes, indeed. 1 comma 2, 2 comma 2, 1 comma 2, okay. 2 comma 1, 1 comma 1, 2 comma 1, okay. 2 and 2 comma 2, 2 comma 1, 2 comma 1, okay. So indeed, yes, this is what? This is reflexive. So one relation is what? One relation will be my 1 comma 2, 2 comma 1, 1 comma 1, 2 comma 2 and 3 comma 3. So one relation is this, and this is indeed by definition you can say that it is reflexive, symmetric and transitive. Okay. Can you make another one, construct another one? So let's see. We use this element. We have used these also. So let's see, and these are the necessary elements. We cannot eliminate any of these elements. We only can add. So as you can see, the what elements we can add, the remaining elements are the remaining pairs are these. Okay, 4. Let us try to add this one, say this one, 1 comma 3. So 1 comma 3, if I am going to add 1 comma 3, then I have to add 3 comma 1. Why? Because the symmetric condition, because my relation must be symmetric. If 1 comma 3 belongs to R, then 3 comma 1 also belongs to R. That's why. Okay, so automatically if you write this, automatically you must have to write this element. So I have used this and this. Now what about the transitivity? Okay, so because my function must be transitive also, as 2 comma 1 belongs to R, 2 comma 1 belongs to R and 1 comma 3 belongs to R, then because my relation must be equivalence. Equivalence means it must satisfy transitive relation, and from here what I can say, that 2 comma 3 must belongs to the relation R, must belongs to the relation R. As you can see, does a 2 comma 3 pair belongs to the R? No. So I have to write 2 comma 3 also. As soon as I write 2 comma 3, by symmetric condition I also have to write 3 comma 2. So 2 comma 3, now I have used this element also, this element also. So now this is my equivalence relation, and I have no other elements that I can use, because every element in this set I have used. So the relation here is also equivalence, and the relation over here is also equivalence. Okay, and you cannot get any other relation apart from these. One is this one, second is this one. Why? Because as you all know, these are the necessary elements. We started from this element, then added this, and then by transitivity added this, and then by symmetricity added this. Okay, you can either start from this, then you will get to know that by symmetric condition you will get this, and by a transitive condition you will must have to add this, and from this by symmetric you must have to add this. So these are the only two possible relation such that containing this pair and my relation equivalence. So the option B, must be the correct option for this question. So for this set A 1 2 3, the set A 1 2 3, then the number of equivalence relations containing this pair 1 comma 2 is equals to what? 2. I hope that it is very clear to you what is happening and how we arrived this and this. Okay, so option B was the correct option. So 2. That's it from my side in this lecture. So thank you for this.